and we had started looking at basically doing comparisons with these paint examples, brand A and brand B, and I think we were working through our standard deviation process over here, I believe. Yeah, we had made it through this example here where we were looking at what was the variance and standard deviation for our brand A paint example, because obviously both our brand A and brand B have the same mean. And so since we have the same mean, that really doesn't tell us much about which brand performs better than the other. So this is where we were kind of trying to show how variance and standard deviation can make a difference. So the first example we looked through was this with our brand A. We talked about how to calculate the variance and then how to calculate our standard deviation. So I actually wanted to do the same calculation here for our brand B set. So let me pull up that data value over here. So yeah, we've got brand B over here. So this is kind of what we had done last time with our brand A. So we calculated our deviation first, then we squared those to get rid of the negative values, add that together, divide by how many total data values we have, which gives you the variance, and then of course taking the square root on that gives us the standard deviation. So let's do this for brand B now. And this time for brand B, again, we would start by calculating our deviation first. So let's see, our data values here are going to be 35, 45, 30, 35, 40, and 25, of course. So again, remember for brand B, our mean is also 35 months. So the first thing we end up doing is subtracting from each one of these our mean, which is a 35 months. Now remember, we are treating this as our population, right? So we are using all the symbols and formulas that we would for calculating the population variance and the population mean. So from each one of these, we would be subtracting our mean from. So subtract 35 from each one of these values. And what kind of deviation are we looking at here? And then of course, our next one is where we square each one of these data values. So what would those numbers look like in our deviation column? Come on guys, it shouldn't take you that long to go ahead and do those subtractions. Okay, let's see, yeah, 35 minus 35 will of course give you 0. You're doing 45 minus 35, so that's going to be 10. 30 minus 35, very good, negative 5. This should be positive 5, and then negative 10. And obviously, you know, if you were to go ahead and add all of those together, the positive 5, negative 5 would cancel each other out, and this should actually be negative 10, not 5. And the positive 10 and negative 10 will end up canceling each other out, which would end up giving you a total of this as 0. And remember, this is the reason why we square each one of these numbers, so that we can avoid this getting a total of 0. So of course, in this case, if you square these numbers, we would end up making our negatives into positives. So what kind of values are you looking at here? Okay, Alexander, let's see, we've got 0, 100, very good, which would be the same for negative 10 squared. Okay, Maya. Negative 25 and positive, negative 5 and positive 5 squared would be 25. And then, of course, 0 comes out to be 0. And what kind of total are we looking at here? Very good, 250. And basically, the formula that we are using over here is this one right here for our population variance. So we're kind of working on the variance right now, and then you basically take the square root of the variance to get your standard deviation. So we've got our numerator, which is the summation of our deviation squared. And then the formula tells us that basically we will need to divide by the total data values we have. So how many data values here do we have? How many paints of can were we trying to test over here? Yeah, very good. We had a total of 6 paints of can. And what does this come out to be as our variance? Tyler, Mercedes, what do you guys have? Yeah, and that's actually going to be a repeating 6 is what you're going to have. So if we just follow our rounding rule, it will usually go for 1 decimal place more than the raw data. So we could say the variance is approximately 41.7, and then of course this would still be in months. But when we talk about standard deviation, remember standard deviation is where, oh, come on, buddy. You take a square root on your variance, so that would be square root. And this is where you do not want to use the rounded answer. You want to keep that repeating for 41.66666. So when you take a square root on that number, what will it come out to be? Yeah, very good. Tyler, so we've got 6.4549 and the numbers just keep going. So using our rounding rule again, this will actually round up to 6.5 months. So you've got your variance and we've got our standard deviation. Now, if we compare this with what we had done last week, you will see the variance is 291.6 or zero point 0.7, and then our standard deviation is 17.1. So just looking between the two brands and comparing that variance and standard deviation, what does that tell us about which brand is performing better in terms of having a better lifespan? Because you know the idea is with standard deviation basically tells us how far away from the mean we are. And of course, this is again an average because, you know, of course, we're taking the total and dividing by the total number of data values we have. So it's actually telling me on an average which number is closer to the mean. And the closer you are to the mean, in this case, of course, that means it's performing better because that means out of all the cans of paint, we are able to get 35 months out of them. So if you are 6.5 months away from the mean, then we are saying you're staying within 6.5 months of that mean of 35 months. But whereas on the brand A, of course, these guys are going in 291 for the variance, but 17.1 months away from the mean. So we are saying you can be, you know, on the lower end, 35 minus 17 months, which will of course put us where at about 19, 18 months or so, which is a really short amount of time for outdoor paint. Or you could be at the higher end, but there's more fluctuation basically in how long this outdoor paint can last. So that basically tells us, you know, obviously that brand B is going to be a better choice because you are going to get more consistency. And remember, we had kind of talked about this last time when we were just looking at the little graph over here, and that again showed us that brand B had more consistency because they were all gathered near the mean, whereas brand A was more spread out. So this was just to show you how this method of calculating your variance and standard deviation works. And then again, we talked about the rounding rule last time. The rounding rule is the same as the mean. For standard deviation, you are always rounding it to 1 decimal place more than what your original data is. So just keep that in mind. So this was the example using brand A. And just some things that I wanted to point out is they're talking about, you know, how the square root of the variance gives you the standard deviation, or basically if you were to square the standard deviation, you would end up getting the variance. So just something to keep in mind, and this is going to be true for all standard deviation calculations. They're telling us the variance is actually the average of the square of the distance from each of the data values from the mean. And so if you kind of think about this as an average, that kind of also helps you determine, you know, when you're doing that comparison, the smaller the average, which means the closer you are to the mean. And in most cases, that means you're performing well, unless your example is of a different kind, and then it may mean the opposite. But, you know, obviously it depends from example to example. So they're saying if the values are nearer the mean, the variance will be small. And of course, the values are farther away from the mean, your variance will be large, like we saw in both our examples here. They are also telling us when you are finding the square root, always use the positive value, because again, if you guys remember this from algebra, square roots of negative numbers, are obviously going to be undefined or basically imaginary numbers. And also, even if you just talk about the calculation of a square root, you can get one positive and one negative root. Even in that sense, they are saying obviously we want to use the positive root because for most of these negative numbers are not going to make sense in a practical example. So again, you always want to use the positive value. And like they're telling you, since the variance and the standard deviation can never be negative numbers. Now here is the example for the comparison with brand B. So again, you will see we take the difference between each of our data values and the X. Go ahead and square them, add them up, divide by your total number of data values. We got 41.7 and 6.5, just like we saw in our example over here. Okay. And you can kind of read the summary over here for this example. So that was the idea of using the population variance and standard deviation. Now, when we get into sample, when you collected a sample from the population and then you try to calculate its sample and standard deviation, there is going to be a little bit of a difference in the formula. Of course, for sample mean, we use the notation of X bar. And then for our sample size, we use the small letter n instead of the capital letter n. But you will also notice in your sample variance formula that on the denominator, we have n minus 1 instead of just n. So that's one difference you will notice from our population variance, where you had, you're dividing by n, but in the sample size, we actually divide by n minus 1. And that's basically to kind of take care of that sampling error kind of thing that you can get between a sample size and a population size. But there's a little bit of a description right here at the bottom of this paragraph here. So basically, they are saying, using the sample mean of X bar instead of the population mean of mu, and the sample size of small letter n instead of the population size of capital letter N, would underestimate the population variance and the standard deviation. And they're telling us because when the population is large and the sample is small, they're saying usually less than 30 in your sample size, they're saying the variance and the standard deviation usually underestimates from what the population variance and standard deviation would be. And to basically kind of make up for that underestimation, they're saying therefore to calculate an unbiased estimate of the population variance or standard deviation, we end up dividing by n minus 1 instead of n. So that's the one difference you're going to notice between those two formulas. And then of course, standard deviation is where you just take a square root of the variance. So same formula, but under a square root function. And of course, your X represents the individual data values. X bar is going to be the sample mean, and little n is going to be your sample size. So just to show you the example over here, they're talking about, again, the teacher strikes in Pennsylvania public schools. And so basically the first thing we would have to do in this case is find our mean, because they didn't give us the mean here. So the first thing we are doing is finding the mean. So take your data values, looks like there's 6 of them, divide by 6, and we get a mean of 8.5. Then of course we would take each data value and subtract the mean from it. So you're finding this difference. So from each of the data values, subtract them. Now, again, if you try to add these numbers together, you would either be at 0 or close enough to 0. So we square these to avoid getting a total of 0. So we square each one of our deviations, add them together, take the sum of the squares, we end up getting 65.5. And then remember, you divide by n minus 1. So there's a total number of 6 data values. We're going to divide by 6 minus 1, which would of course give us 5. And this is our variation of 13.1. Taking a square root on 13.1 will give us the standard deviation of 3.6. So this is your variance for the teacher strikes. And this one is going to be the standard deviation over here. So we have a number of standard deviation of 3.6 when our mean was 8.5. And so in this case, you can kind of say, okay, we are a little bit farther away from the mean, but if you were doing a comparison, it would actually make more sense to see, which data is performing better than the other. So in this case, it just actually tells you what the standard deviation is with respect to this mean of 8.5, and looks like we're coming up with approximately 3.6. This method that we have done so far is actually longer and more tedious. And as I was explaining to you guys last time, what if you had a data set of 50 items in it, or maybe even 100 or more than that? That's going to be a lot of individual subtraction we have to do, then square each of the numbers, and then get our total and that sort of thing. So we actually end up using these shortcut formulas for doing our calculation. So we don't actually use the longer method, but this is the method we are going to use, and this is the method we're going to stick with for all our calculations. So they're telling us that basically both these formulas are mathematically equivalent. You will get the same result. The difference in this shortcut method is you don't have to exclusively find the mean for your data items, because the way this formula is designed, it's actually built into it. So you don't have to find the mean separately, which is what we had to do in this example here with the teacher strikes, because they didn't give us the mean. So that would be the first step we would have to perform. And you don't have to do that here in this case. So you will notice for the variance on the numerator, we have n multiplied by the summation of x squared. So this is taking the square of each data item, adding them together, minus this one here is you add all the data items together, and then you take the square on that total. And then of course we are dividing by n times n minus 1 on the denominator. So you can see in this note here, we are saying the summation of x squared is not the same as when you put the square on the outside. When you are doing summation of the x, the whole quantity squared. So this little note here is just kind of explaining the difference between these two notations. So this one here, summation of x squared, means you square the values first, then add them together. The one with the parentheses where you have summation of x and then the whole thing squared, it means that you add the values first and then square that total, that sum. So going back to our teacher strikes example, and you will see these are the same exact data values, 9, 10, 14, 7, 8, 3. We've got 9, 10, 14, 7, 8, 3. So same example. But now what you have to do is take all the data values, add them together, get this total. We take the square of each of the data values and then add them together, and you get this total. So that's the difference between these two notations. And then what we're actually going to do in our calculation is then square this number, because this is the second part of our formula. Okay, so you can see we have n, which is 6 data items, summation of x squared, which was the second step we did, 499. So that's where that's coming from. The minus summation of x and then the whole thing squared is step 1, which was the total of 51. And then you end up squaring that. And denominator is 6 times 6 minus 1, or basically 6 times 5. And you will notice we're getting that same variance of 13.1, and when you take a square root on that, we get a standard deviation of 3.6. So 13.1 and 3.6, and you'll notice those are the same exact numbers, but a lot less steps involved in solving the same example by using the shortcut method. Let's take a look at the shortcut method and see if we can do an example here so you guys can get a little comfortable with that process. So let's take a look at there we go. I want to keep it simple. I don't want to do. Well, let's do the cigarette taxes example over here, number 18. Sorry, number 8. They're talking about the increases in cents in cigarette taxes for 17 states over a 6-month period. They're asking us to find the range, variance, and standard deviation. We'll come back and talk about the range rule of thumb because we haven't done that as of yet, but let's use the shortcut method of trying to find the result for number 8 over here. So they're asking us to find the range So what is our lowest data value over here? And the highest data value. Okay, 8 is the lowest one, very good. And the largest data value? 69. Okay, Tyler, you've got 70. Anything larger than 70? Doesn't look like it, does it? Okay, so your range would of course be the largest data value minus the smallest one, and what does that come out to be? So what is 70 minus 8? Yeah, 62. So this is a range of 62 units. Okay, let's talk about its variance. Again, remember we are going to be using the shortcut method. Let me go ahead and put our formula down. So this is going to be s squared equals n times summation of x squared minus summation of x, the whole quantity squared, divided by n times n minus 1. Okay. So let's see, our n value, they're telling us it's for 17 states. So that should be our n value, but all you have to do is just count how many data values you've got. And of course, you'll see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So that's just the quickest way of verifying that you will in fact have 17 data values over here. And let me clear this out because we don't really need that. So our n value is 17. Now the first thing we are going to do is just go ahead and add up all our data values. So just go down the line and let's add up that total, and what does that come out to be for all our x values. Lisa, do you have that number for me? Yeah, very good, Alexander. It does come out to be 652. Now, the next step is going to be where we have to actually individually square each one of these. So that would be, let me see if I can try and get this on the same screen. So this is where we would have to take the square of each individual number and then add them together. So what will this total come out to be? Now this will be a pretty large number because obviously you're going to square each one of these quantities and then add them together. Okay, so let's see, Alexander and Tyler, you guys have 30,334. That's what I got. Alrighty, very good. So let's see, we have this number, which is of course the 30,324, and then we have this inside number, which is the 652, and then of course we know our n is going to be 17. So let's put it all together for our variance. Oops. Okay, so our number is n17. Summation of x squared is the 30,324 minus summation of x was 652, which we will need to square now, divided by, which will be 17 times 17 minus 1. So let's do 17 times 30,324 first. Looks like that's coming out to be 515,508. Now, what will be the square of 652? Again, you're taking a square on a 3-digit number, so that should be pretty high. 425,104, so 425,104. And here's the key, guys. If these numbers don't come out to be like, both of them are figure numbers, 6-digit numbers, and pretty close enough, then you know something went wrong in your calculation. So always be careful about that. Of course, your denominator will be 17 multiplied by 16. So let's take the difference on the top, and what does that come out to be? Okay, so take the difference on the top, multiply the denominator, and then of course, when you do that division, the answer will be the variance for this data set. So when we subtract 515,508 and 425,104, looks like that difference is coming out to be 90,404, and then 17 times 16 is coming out to be 272, right? So what will your variance end up looking like? 332, 38. Okay, Maya, Alexander, you guys seem to be off by a 10. So let's see what this comes out to be. Okay, so 332.367, yeah, 471. So what Maya had is what I got. Okay, so this is going to be your variance. And again, you will notice, since this is a sample size, we use the letter S for our variance and standard deviation. So standard deviation would be taking a square root on this number. And what will that come out to be? And of course, if you round this number up, 18.2, Alexander, okay. Yep, very good. the standard deviation of 18.2. Let's go back to our example here. It looks like Tyler, you came up with the same result. Okay, very good. Alrighty, so you can see this was talking about the increase in terms of cents on cigarette taxes for a 17-month period. So as you can see, we did not have to calculate our mean. Now, of course, if you were going to do a comparison or something, you could calculate the mean. But as you can see in this process, we went directly to just calculating our variance. So we have our summation of x squared, which came out to be the 30,324. Summation of x, just adding all the x values, came out to be 652. And then our total data items of 17, we were able to put that directly in, came up with our variance, and then you have your standard deviation by taking a square root. So this formula over here really does work a lot quickly than taking each data value, subtracting the mean from it, and going through that whole process. So again, for the exams and everything, I would recommend you guys to use the shortcut method. Now this next formula over here is of course for grouped data. So where you have frequency distribution tables with grouped data, how would we go about performing these calculations for variance and standard deviation? So as you can see, this will be very similar to what we had done for the mean calculation. But in this case, again, we are going to skip finding the mean and go directly into calculating the standard deviation and of course the variance. So remember, the symbol x sub m is basically talking about the class midpoint. So for each class, we would have to find its midpoint. Then you take the square of the midpoint, multiplied with the frequency, and then we add up the total. And that's going to be for the first part. For this summation of f times xm, you are basically just taking the single midpoint. You're not squaring it. So just the midpoint, multiply by the frequency, and then add all of them together. And that total, you will then end up taking a square on that later on. And then, of course, you are dividing by n times n minus 1 here. And on that first part, again, we are multiplying by n. So very similar to this shortcut formula that we looked at here, but the only difference is for the calculations, we will need to multiply the midpoints with the frequency, and in some cases, of course, we need to do a square before we multiply. Taking a square root on the variance will again give you standard deviation. So they're just kind of listing those steps here in this procedure table. But again, just to show you an example quickly, we're talking about finding the sample variance and the sample standard deviation for the frequency distribution. And the data here is basically representing the number of miles that 20 runners ran during 1 week. So you're basically going from 5.5 to 10.5 miles, and there was just one runner who ran that many. From 20.5 to 25.5, there were 5 runners who ran that many miles during the week. So that's kind of how this table is set up. And then, of course, you can see there's an overlap happening in our classes, which tells you these are actually class boundaries that they have given us. So find the midpoint for each class. Now, remember, there are 2 different calculations we have to do. So we have our class, we have our frequency, we have our midpoint. Now, for this first column, which is column D, you are multiplying the frequency with the midpoint. So you're basically just multiplying 1 times 8, which will be 8. 2 times 13, of course, will be 26. And we'll go ahead and do all of those calculations. So you will see that's our D column. Now for the E column, we will first square our midpoint. So that would be 8 times 8, which would be 64. And then 64 times 1, which would be 64. Same thing, 13 times 13 would be 169. And then we would double 169, which comes out to be what, 338. And then that's how we would go ahead and complete the rest of the columns. So that's how you actually go ahead and calculate those two. Then we would have to take the total for each D and E columns. The D column total is going to be the second one over here, which we need to take a square on afterwards. And the E column total is going to be for this first parentheses over here. So again, you will see we are talking about 20 runners, or you can basically add up the frequency column to get your N value. And then we multiply by 20 and 13,310, that gives us the first part. You take the square of 490, and then of course denominator is 20 times 20 minus 1, or 20 times 19. Going through that math, we come up with our variance, and then take a square root on the variance, and it gives you your standard deviation. So that part is just going to stay the same. Calculation part pretty much stays the same. It's just how you calculate your D and E columns. That's the only part that's going to be different between just having single data values or having a group frequency distribution. Okay, so let's take a look at an example here for a group frequency distribution. And I guess we can do number 11 over here. They're talking about the following frequency distribution shows the average number of pupils per teacher in the 50 states of the United States. So the average number of pupils per teacher, and they're basically asking us to find the variance and the standard deviation. So as you can see over here, we've got our class limits, we've got our frequencies. So of course, the next column that we need here is going to be our midpoint. So frequency is the F column, midpoint is the X sub M. So what will be the midpoint for each of these? Classes, I guess. Okay, let's see, Alexander, you've got 10, 13, 16. It looks like Tyler, you have the same answers. 19, 22, and 25. Yeah, I mean, literally it's the number right in the middle of those class limits, or you can think of these as being in increments of 3. All right, so we've got our midpoint now. So for our next column, we will go ahead and multiply the frequency with the midpoints, and then we'll do another column where we multiply the frequency with the square of the midpoints. So of course, the first one we are multiplying 10 times 2, which will of course give us 20. And then let's see what those other numbers come out to be. So 20 times 13, which would be basically the double of 13 is 26. So add a 0 to it, you get to 60. Now let's see what those other numbers are, guys. Okay, we've got 228, 133, 2 times 22 is 34, 25. Okay, now let's talk about the total for those. 770, okay. And can somebody else verify that total for me, please, just to be sure? Now for the last column, remember this is where we would be taking basically the midpoint, squaring it first. So you would basically be doing 2 times 10 squared, or basically 2 times 100, which would of course give us 200. For the second one, we would be doing 20 times 13 squared. That would of course be 20 times 13 squared is 169. Alexander, your total came out to be 710. Okay, let me see. Something. 260. Oh, right there. Okay. Alexander, you had 228. 18 times 16 should be 288. This is where we were having trouble. This should be 288. So that would be now 4, 18, 19, 20, 21, 27. So 2, 4, 5, 6, 7. Yeah, it should be 770. So yeah, you were missing 60 points. No, not a problem. Alrighty, so let's see, what are we getting here on our XM squared? So when we do 169 times 20, that will come out to be 338, and then we can put a 0 at the end. 18 times 16 squared, 7 times 19 squared, 3 times 22 squared, and let's see, I guess 1 times 25 squared would be 625. Mm, 20, 48, 25, 27, 968. Okay, and then what does that total for that column come out to be? I'm not sure about that 2048 because 18 times 16 squared, yeah, that should come out to be 4,608. Yeah, 4,608, 25, 27, 968. So just that one number, Alexander, be careful about that. And what are you getting the total for that last column? $12,308. And that's what I was also able to come up with. All right, so we've got all our preliminary numbers taken care of. Of course, they're giving us the total of the frequency column, which will of course be our n value over here. So now that we have all of these, we can go ahead and do our calculation. So let me save our screen over here. And I'm going to try and keep these numbers for a minute, and then once we have it copied over, I'll go ahead and erase them. So let's see. I guess that was number 19. We have our n value as 50. The summation of the frequency times midpoint is 770. And summation of frequency times the square of the midpoint is 12,300. Okay, so we can go ahead and clear this now. All right, so again, guys, our formula here for the variance is s squared equals m times summation of f times xm squared. Make sure I have that right. Yeah, xm squared, and then minus the summation of f times xm, and then the whole quantity squared over n times n minus 1. So we are looking at 50 times the summation of xm squared would be 12,308 minus the summation of fxm is 770. Then we square that, divided by 50 times 50 minus 1. So let's go ahead and clean up that numerator. So if we multiplied 12,308 by 50, we are again getting a six-figure number, which is 615,400 minus the 770 squared. Again, make sure this is large enough number compared to that first one you just got. So this one's coming out to be 592,900. And then of course your denominator would now end up becoming 50 times 49. So let me see what you guys are getting as your final answer. for your variance. So what will this end up giving us? 9.18, okay, so let's see. The raw answer was 9.183673, and it keeps going. Using our rounding rules, let's see our data value, our whole numbers, because our class limits are whole numbers. So you can round this to 1 decimal place, 9.2 on our variance. And then what's the standard deviation? Keep all those decimals when you are taking the square root. Do not use the rounded answer. So this is coming out to be 3.03045, and it keeps going. So by the rounding rules, what should our answer be here? Yeah, because when you use the rounding rule, which would be 1 decimal place, the 3.03 will basically just end up becoming 3.0, which would of course just come out to be 3. That's going to be your rounded answer for this guy. So this was just to show you how with a grouped frequency distribution, what our answer can end up looking like. And this was, of course, for number 19 over here. And again, guys, you should obviously make the observation that we did not have to worry about finding the mean again for this data set. We were able to calculate the variance and the standard deviation without finding the mean. So this was our standard deviation. Any questions on this example here? You guys doing okay on this? Yeah, okay. Let's get back to our handout. So of course you can see they're giving you the summary for the different measures of dispersion over here, the range, variance, and standard deviation, and then of course using the symbols for population, and the S is of course the symbol for the sample calculations. And again, they're talking about the different uses of variance and standard deviation over here. So this is a pretty good read. I would definitely ask you guys to kind of look through this. They're talking about, you know, how variances and standard deviation basically help us determine the spread of the data. If the variance or standard deviation is large, the data, of course, is more spread out or more dispersed, right? And this definitely helps if you are comparing 2 or more data sets, because then it kind of helps us to see, like we did with the paint examples, which one turns out to be a better product or a better data set. They're talking about the measures of variation and standard deviation are used to determine the consistency of a variable. So they're talking about, for an example of the manufacturing of fittings like nuts and bolts, obviously in this case you want, you know, if you're making one particular type or size of nut or a bolt, you obviously don't want the variation to be too large, because you want the variation to be basically in micro numbers, because, you know, obviously you want all those measurements to be equally the same. So they're saying the variation in the diameters must be very small, or otherwise the parts will not fit together. So again, variance and standard deviation can be used in those type of measurement calculations. They're also talking about the variance and standard deviation are used to determine the number of data values that fall within a specified interval. And this is actually the basis for, like they're talking about here, the Chebyshev theorem, but also in terms of Bell shape distribution, right? Your normal distribution, which is again something we'll be talking about later on. So they're saying, for example, in Chebyshev's theorem, it shows that for any distribution, at least 75% of the data will fall within 2 standard deviations of the mean. So we're basically saying wherever your mean is, if we go, 2 standard deviations out, which means 1 standard deviation would be just taking the standard deviation and adding and subtracting from the mean. 2 standard deviation means you do it twice, so you double that quantity, and within that range, we will have 75% of our data fall in that, and we will be talking about that later on. Now, the next thing we actually want to talk about is the coefficient of variation, as you can see here. So they're saying whenever you have 2 examples that have the same units of measure, they are saying variance and standard deviation can be compared directly, right? So if, let's say, both the paint examples were talking in terms of months. Now, if you had one of them talking in terms of months, but maybe the other one talking in terms of maybe weeks, then your measure, the unit of measurement would be different. And then it would be hard to make a comparison using variance and standard deviation. So like they're talking about, for example, here, suppose an auto dealer wanted to compare the standard deviation of miles driven for the cars she received as trade-ins on new cars. So she's saying she found that for a specific year, the standard deviation for Buicks was 422 miles, and the standard deviation for Cadillacs was 350 miles. She could say that the variation in mileage was greater in the Buicks, and of course we can see that because the Buicks have a larger number. But they are saying, what if the manager wanted to compare the standard deviation of 2 different variables? And your variables could be the number of sales per person over a 3-month period and the commission made by these salespeople. So now you are talking about comparing the number of sales to how much commission they were earning, right? So those are not the same units of measurement. In that case, we bring in this idea of coefficient of variation. So they're basically saying a statistics that allows you to compare standard deviation when the units are different. And we denote this by C bar, or basically for your coefficient of variation, they are saying is the standard deviation divided by the mean. So you will see for samples, we're taking our standard deviation X, dividing it by X bar, and then we of course multiply this with the percent because we always talk about coefficient of variation in terms of percentage. For population, we would be taking standard deviation of sigma, dividing it by mu, and again multiplying by 100. So just depending on, are you looking at a population or a sample, the formula would be a little bit different, but essentially the same calculation. So just as an example here, number 9, we've got the mean number of sales of cars over 300 period is 87, so that's our mean. The standard deviation is 5. They're saying the mean of the commission is $5,025 and the standard deviation is $773. So this is, the example we were talking about here. If the manager is trying to compare number of sales to the commission earned by the salespeople. So for the first one, we are taking 5 as a standard deviation for the number of sales divided by 87, which was the mean, and that's coming out to be approximately 5.7% in sales. With the commission, you had 773 as a standard deviation, divided by the mean of 5,225, and you can see that one is coming out to be 14.8%. So we are saying since the coefficient of variation is larger for the commissions are more variable than the sales. So we're basically saying these salespeople earning their commission based on how many cars they are selling is more variable or more spread out or more dispersed than the sales. So your sales are actually more consistent and the commissions are more varied, okay? We've got a roller coaster example here. So they're talking about the mean speed for 5 fastest roller coasters is 69.16 miles per hour. The standard deviation, the variance for them is 2.76. The mean for the height of the 5 tallest roller coasters is 177.80 feet, and the variance is 157.70. So notice that they are actually using variance over here and not standard deviation. That's why they are doing those square roots on the numerator. So you've got square root of 276 over the mean of 69.16. Convert that to a percent and it's coming out to be 2%. And this one was for the speed of the roller coasters. For the height, we have a standard deviation which would be square root of 157.70 divided by the mean of 177.80, and again convert that to a percent, and this is coming out for the height as 1%. So again, we are saying the variation in the speeds is slightly larger than the variation in the height of the roller coaster, because of course that one is at 2%. So of course you're comparing speed, which is in miles per hour, to height of the roller coasters, which is in feet. So again, two different measurement units of measurement, and so again, the coefficient of variation is what we need to use in this example. So let's do a quick example on the coefficient of variation. And then I do want to talk about the range rule of thumb so we can go back and compare it to that first example we have looked at. So these are all. Okay, we can take a look at number 27 over here. So 27 is talking about the average number of days that construction workers miss per year is 11. That's your average, so that's going to be our mean. The standard deviation for that is 2.3, and this was for construction workers. The second part is saying the average number of days that factory workers miss per year is 8, and they have a standard deviation of 1.8, it looks like. So they want to know which class is more variable in terms of days missed in this case. Okay, so let's take a look at this example here. Let's do the C variance or coefficient of variation here. And I'm going to say these are sample. Okay, so we'll use this. So let's do the construction workers. So we have, for the construction workers, the standard deviation is 2.3. And the average number they're telling us is 11. And of course, we multiply that by 100. For the factory workers, let's see, they're telling us the standard deviation is 1.8 and the average number of days missed is 8, and again converting that to a percent, what kind of percents are we getting for our coefficient of variance over here for the two types of uh, working people here? And we'll round all our answers to 1 decimal place to keep up with the other example we saw. Okay, Maya, I'm guessing you have 20.9 for the construction workers and 22.5 for the factory workers? Okay, so let's see, 2.2 divided by 11 multiplied by 100, rounding to 1 decimal place, we have 20.9%, okay? And then we are doing 1.8 divided by 8, and then of course multiplied by 100, which will again approximately be 22.5%. Okay, so our question is, which class is more variable in terms of days missed? So which class would you say is more variable here, guys? So out of the factory workers and the construction workers, which one would you say is missing more work, I guess, in terms of, okay, Tyler, yeah, factory. Yeah, because the factory workers have a larger percentage value than the construction workers, right? So yeah, we would say factory workers are more variable than the construction workers. And this is of course based on how many days they are missing. But as you can see, it's a very simple calculation. But the one thing is going to be is identifying that they are asking you to do this. And as you can see, they didn't specifically say use the coefficient of variation. In this case, they basically said, here's the average and the standard deviation for one group. Here's the average and standard deviation for the other group. Find out which class is more variable. So you kind of have to look for those sort of wordings to help you out here. Okay, so that's your coefficient of variation calculation. Now, the other thing I wanted to talk about, and this is again an approximation, but this helps us kind of approximate what the standard deviation could be. So they are saying you can use the range to approximate the standard deviation, and that's why we call this as the range rule of thumb. So you can see we take the range and you're basically dividing it by 4 to get an approximation on the standard deviation. So if you look at this example over here, they have the data set 5, 8, 8, 9, 10, 12, and 13. They are saying the standard deviation is 2.7, and the range is, of course, just 13 minus 5, which gives you 8. So if you take that number 8 and divide it by 4 by using this range rule of thumb, of course, you will see that gives you the number 2. And this is just going to be an approximation on our standard deviation. Now, of course, you can see the standard deviation is actually 2.7. So the number 2 gets you close enough. And that's why we always say this is an approximation, because it obviously is underestimating than what the actual standard deviation is. But like they're saying, it's getting you within that ballpark of the standard deviation. So they're talking about a note of caution. They are saying the range rule of thumb is only an approximation. okay, and should not be used when the distribution of data values is unimodal or roughly symmetric, because when your data is unimodal or roughly symmetric, accuracy can be definitely an issue in that case. So they're talking about the range rule of thumb can be used to estimate the largest and the smallest data values of your set. They're saying the smallest data value will be approximately 2 standard deviations below the mean, and the largest data value will be approximately 2 standard deviations above the mean. And they are saying the mean for the previous data set is 9.3. So they're talking about this data set over here. And they're saying approximately the mean for that data set is 9.3. So what you can do with this range rule of thumb value, which is this number 2 over here, take the mean for the data set, which is 9.3, and then you add and subtract 2 times 2 to get your approximate largest and smallest data value. So you can see when we add and subtract basically 4 from that 9.3, we get 5.3 and 13. And again, you can see 5.3 is pretty close to this number 5, which was the smallest data value. And that 13.3 is close enough to this largest data value they had of 13. So again, this range rule of thumb can kind of help us approximate what the smallest and the largest data values will be. And you know, a lot of times this is just a quick way of seeing, okay, what do these calculations need to be, you know, without having to do that entire long process. So they're saying the smallest data value of 5 and the largest data value were 13. Again, remember, these are just your rough approximations. They are saying for most data sets, all data values fall within 2 standard deviations of the mean. And of course, you can get better approximations from the Chebyshev rule or the empirical rule. So before we move on to Chebyshev, I wanted to come back to this example we did initially. Yeah, right here with the cigarette taxes. They had asked us to use the range rule of thumb to estimate the standard deviation. So let's go back and look at these calculations for number 8. There we go, number 8 over here. So now let's talk about the range rule of thumb. Again, remember the formula is you get the standard deviation approximately by taking the range and dividing by 4. So our range is 62. 62 divided by 4 is what? So 62 divided by 4, 15.5, okay. So 15.5 is an approximation for a standard deviation. Now let's see, what did we get for the standard deviation here? You can see our standard deviation was 18.2. So we are, again, like we said, in the ballpark, but obviously not quite at the same number. So 18.2, and with our range rule of thumb, we're coming up with 15.5. Now, if we wanted to calculate the approximate smallest and largest data value, for the smallest data value, we would take our mean for this, and then you would do minus 2 times this standard deviation from the range rule of thumb. For the largest data value, we would have to again take the mean and add 2 times, again, this range rule of thumb, which is 15.5, and hopefully we would be somewhere near number 8 and number 70, but obviously since we did not calculate the mean for this set, I'm not going to spend time doing that, but that's basically the idea. You take your range rule of thumb, the S value, and you can use that to approximate what these values are going to be, okay? So any questions on that? And they're basically saying just compare the estimate to the actual standard deviation. And of course, like I said, you know, we're close enough, but obviously not accurately at the same number as what we get from the big long calculation over here. So any questions on the coefficient of variation or on using the range rule of thumb? You guys okay so far? Yeah? Okay. So the last part of section 3.2 actually talks about what we have here as the Chebyshev's theorem. And this one again is, you know, basically just kind of helping us to see what the spread of our data is. Now, Chebyshev's theorem basically can be applied to any data set, to any kind of distribution, like they're talking about here. The variance and standard deviation of a variable, of course, measures the spread or the dispersion of the variable. They're talking about the larger the variance or the standard deviation is, the greater the dispersion is, and we've already talked about that previously. They're saying the smaller the variance or standard deviation is, of course, your data values are less dispersed, and basically the data values are going to be more consistent. So they're talking about Chebyshev, which was, as you can see, developed by a Russian mathematician. This actually talks about the proportion of spread in terms of our standard deviation. So you know how we were mentioning within 2 standard deviations of your mean, so 2 standard deviations above and below from your mean, 75% of the data values are actually going to fall within a range of those numbers. So your Chebyshev's theorem is saying the proportion of values from a data set that will fall within k standard deviations of the mean will be at least 1 minus 1 over k squared. So they're basically giving you 1 minus 1 over k squared, where basically k is going to be a number greater than 1, and k does not always have to be an integer. So k can end up being a fraction or a decimal value also, but that just tells you how far away from the mean you are on the upper and the lower end of the mean. So this one is saying this theorem states that at least 3/4 or 75% of the data will fall within 2 standard deviations of the mean. So what we mean by that when they talk about these, let's say this is just our number line over here. Let's say our mean, and I'm actually going to use the same example that we had here. So let's say our mean is 9.3. So that's the mean. We've got our standard deviation, which was 2.7. So the mean is 9.3. Standard deviation is 2.7. So if I take this number 9.3 and I add 2.7 to it, I will of course end up getting, what will that be? 12. And then if I subtract 2.7 from my 9.3, what will that come out to be? 7, 6 point something? 6.6. So this is what we would say within 1 standard deviation from the mean. Okay, so you would be within 1 standard deviation. So all the data values that you have, which would be from anywhere from 6.6 to number 12, are going to fall within this range. So if you look at our data over here, you had 5, 8, 8, 9, 10, 12, and 13. So of course, the 8 to 12, these numbers would be falling within this one standard deviation of the mean. Now, if you wanted to go 2 standard deviations, I would take 9.3, and then I would do 2 times 2.7 and add that. I would do 9.3 and subtract 2 times 2.7. The other thing you could do is just add 2.7 to your 12 and subtract 2.7 from 6.6, and that would also give you 2 standard deviations. So then we could go 2 standard deviations, which will of course give us 12 plus 2.7 will put us at 14.7. 6.6 minus 2.7 will be what, 3.9. So this is now what we would say within 2 standard deviations from your mean. Now this is 2 standard deviations, and what Chebyshev's theorem is basically saying that 75% of all your data value will fall anywhere from 3.9 to 14.7. Now, as far as our example is concerned, from 3.9 to 14.7, that's actually going to include our entire data set, because our data set goes from 5 to 13. So in our case, it will actually be all 100%. But what Chebyshev says is that you should have at least 75%. Now, of course, you can be more than that, but you should have at least 75% of your data set within those 2 standard deviations. Now, you can, of course, go even more than 2 standard deviations. So if we went 3 standard deviations from the mean, they are saying at least 8/9 or 88.89% of your data items would be falling within 3 standard deviations. So if you go 3 standard deviations out, you would be looking at higher numbers, which of course does not apply in our case because we don't have any more values. So this guy here would now be 1.2. And then of course we are doing 14.7 added with 2.7, which would of course put us at 17.4, and this would be 3 standard deviations from our mean. This would now be 3 standard deviations from the mean. And this is going to be something, guys, we will be revisiting when we do the empirical rule, or when we talk about the normal distribution. We will be coming back and looking at this spread, but the spread kind of changes with normal distribution than what it does with Chebyshev's theorem. And in Chebyshev's theorem, this little relationship that we have with 1 minus 1 over k squared is going to be an important part of how we calculate how far away we are from the mean. So we'll get into calculations next time. So again, if you haven't started working on your homework, please start looking through homework for chapter 3. And our goal is going to be to finish chapter 3 this week, okay? All right, everybody, have a wonderful day. If you have no questions, I will see you tomorrow in class. Be careful, and I will see you tomorrow. Bye, everyone. Bye.